Okay, now that we understand the components, let's talk about how radios actually operate. So once we have the system built up, whenever you key the mic, what happens? And this is if you really want to kind of differentiate yourself from your average A&P. This is an area where if you apply yourself and you really learn it really, really well, and you're not going to be able to learn it over me just telling it to you, even if you were sitting in class, it would be a lot for me to unpack onto you. You really need to get like the art of electronics. You need to get like your NCAT, AET certifications. Just basically a test. You study it, and you go and learn how you go and you learn how to be like an old school avionics technician. I would highly encourage you to get into doing Arduinos. We're going to try to integrate those into class, but effectively you will learn how to build. You can build radios. You can build all sorts of things with Arduinos and Raspberry Pis. If you kind of get into that those skill sets and understanding how that how those systems operate will translate very well over into just bigger systems that are certified. Another thing that I would encourage you to do is like learn how to code. You can do it for free online now. It's very, very easy. The reason being is that a lot of these systems are getting more and more digital, and they're getting more and more integrated. As they get more and more integrated, the code in which that they operate with will become more and more important. The more complex the systems get, and the more complex the aircraft that you work on. So having a good solid base of both like electronics, troubleshooting, manufacturing, all that good stuff, and then being able to understand how a digital computer thinks and operates and arranges things will help you a lot.
Okay, so first let's start off this little venture into just trying to understand what a radio wave is. Now, the graphic in front of you is it's the electronic spectrum. So that means that anything from visible light, which you can see it's clearly labeled there over 10 to about the 14th and a half, I guess, if you want to try to put a spot on it. Anyways, you have like all of these different electronic signals or states of energy, or however, whatever the right physics term would be, electromagnetic waves. And so on the far left end, you have gamma ray radiation. Not really good for you, causes a lot of cancer. Really short wavelength, high frequency kind of energy there. It usually progress to the right. There's your X-rays. So if you go in there, break your arm or whatever, and they're going to X-ray you, that's the wavelength and the frequency in which that light that you can't necessarily see, but will absolutely penetrate your body and cast a shadow on a piece of film to let you know what's going on with what's going on on the inside. And we actually use X-ray. If you remember back to our NDI stuff, we actually use these in different types of non-destructive testing. You have ultraviolet light, so that'll cause your sunburns. Even though you can't see ultraviolet waves, they're out there. You can spend a day out on the beach, and you'll come back in with the evidence of the ultraviolet waves. We have our visible light, and then infrared. If you've been paying attention at all to all the military technology that came out over the 20 years of the global war on terror, your infrared, remember like your white hot, your black hot videos of like gunships engaging targets and things like that. That's all infrared stuff. And like if you ever go work in the military side of aviation, this particular spectrum of light will become like really important to you, because there's a lot of landing lights that are infrared. There's position lights that go on helicopters and airplanes that are infrared. And the reason being is that like you can use the benefits of the night vision goggles because they can see infrared, and it's like the lights are turned on and everyone can see everybody. You get all the benefits of lights, but if you don't have NVGs on, then you can't see anything. And so like it looks like it's just totally black because our eyeballs are not optimized to be able to see the infrared spectrum. But as we progress on, we cross this little threshold at 10 to the negative 1 there, we start getting into radio waves. Now, those radio waves, they start off with ultra high frequency, or UHF. They progress on to VHF, or very high frequency, and then on to HF, which is high frequency, and then MF, LF, VLF. We don't really ever see those, but it's more the same continuation, the same nomenclature of the F is always frequency, and I'm guessing M is mega and L and VLF, but it never gets used. So the point being is that, like, on the bottom part of that spectrum, you have the frequency, which we're going to talk about here in a second, what frequency is, and on top we'll talk about the wavelength. We've talked about that a little bit before in our intro to electricity class, and we're going to give it a little review here in just a second.
Okay, here we are back on our whiteboard again for a real kind of quick recap on frequency and wavelength. All frequency is every time we get a peak, how fast do those peaks happen. So a high frequency would mean that those peaks are squished together because it's happening rapidly. A low frequency wave, it means that they're extended way out. That gets back to wavelength. So the wavelength is just the distance between those two peaks, all right? So you have frequency is how fast it's happening. Wavelength is like the literal measure of, like, okay, well, here's this one. We're waiting. There's the next one, all right? So that's the wavelength between the two waves. So high frequency, short wavelength. Low frequency, long wavelength. Really, really easy stuff.
Okay, so now that we've had that conversation, you can look at the spectrum again and see that on the shorter wavelengths, you have a higher frequency, a number of waves per second. But on the longer wavelengths, on the more useful end in terms of like radio, we have a much lower frequency, and that will continue to be a theme as we go forward. We talk about the different types of radios and different types of systems that we're going to be working on. Okay, so let's look at this graphic that you got on the screen right now. On the left-hand side, you have your different frequencies, your radio frequencies. Now, we take that spectrum from 300 gigahertz at the very top all the way down to 3 kilohertz. And remember that you have the metric prefixes of giga, mega, kilo, and you can look up in our number systems class what all those mean, if you don't know it, or you can Google it. But notice that that's the amount of times those peaks are hitting inside of 1 second. So 300 gigahertz, which is like a lot. It's just wearing that 1 second out with 300 giga peaks, right? Down to 3 kilohertz, which is just like 3,000 peaks inside of a second, which sounds like a lot, but it's really not in terms of radio waves. But anyways, we will attach these different acronyms, or I guess abbreviations would be the right word to say it. Like, you'll hear HF radio, or VHF radio, or UHF radio. Now, you never hear EHF or SHF or MF or LF. Doesn't necessarily mean that they don't get used, but you never hear people say that type of thing. The most two common ones you'll see is VHF radios, and then you'll see HF radios if you start doing stuff over the water, like over oceans, or in areas where there's not a lot of radio monitoring, there's no radar, and the only way to keep track of somebody is using HF radios. So that's kind of oriented to that side. Now the other side, let's aviation uses. We're just going to go start from the bottom, and we're just going to work our way up and talk about these different frequencies and the different implementation or different devices that use them. Okay, so LORAN C is at 100 kilohertz. LORAN is an old navigation technique or device. We won't talk about a lot about it right now. We're going to wait till we get into a little bit further on to really kind of break down what LORAN is. The so what of LORAN, though, is that you generally don't see it anymore. It's possible, I guess, that you could probably come across it. I never have. It was kind of a thing back in the 70s, 80s that got pretty quickly replaced with more appropriate or more, I guess, effective radio navigation aids, like the ADF. So ADF is an automatic direction finder. You'll see those pretty. They're still even in 37s. In the MMR, the multimode receiver, can receive a lot of different radio spectrums or a lot of different frequencies, and so they still have the ADF capability, though you don't really see it getting used just a whole lot, but it can be, and you'll see ADF pop up on the screen if it ever does. NDB is a non-directional beacon. It's just like a homing beacon. AM broadcast. Now this is where this one gets really interesting. Kind of like an old trick is that your ADF, if you can pipe it into a headset and like hear what the ADF is putting out, you can also listen to AM radio on it. So I used to listen to Sherlock Holmes on the KC-46 whenever I was doing like avionics pre-flight. I turned the ADF on and put it on the headset or on the speakers in the cockpit and just enjoy listening to. It was either Sherlock Holmes on the NPR station there, or we would listen to. There's a gospel radio that was like really kind of over the top. That was within range of where the airfield was, and we would tune the ADF into that. But notice that the frequency overlap. The ADF will go from 200 kilohertz all the way up to 1600 kilohertz. Your AM broadcast station will go to 550 to 1800. Now, back in the day, you'll talk to old guys that would say they would used to kind of navigate using the ADF. They would basically tune into a radio station where they knew something was at. So, like, say if you were flying to Texarkana, you tune into I think it's like 790 or something. This is what our NPR station is here, and you would basically aim the needle at that, and then you would listen over the radio to hear if it was coming in clear or more broken. And then by the time it was crystal clear, you're basically over the station. Then you would tune to the next one and keep on going. That was a way to navigate, and that's kind of like way back when. But there's still people that are alive that remember doing that. Okay, so the next one up is our HF radio. Due to its high frequency, long wavelength, HF carries a lot further than VHF. The downside is it's not nearly as clear. So if you can think of that, like those frequency peaks are almost like data points. So like if I really wanted to understand, if I wanted to measure like my truck, and I went and said like, okay, well the truck is 20 feet long. All right, that's all I really know is it's just 20 feet. But then if I had like another data point, I said, oh, but it's also 6 feet wide, and it's also like, and I keep on taking these different measurements. All of a sudden, I can kind of like build a three-dimensional model in my head of what that truck looks like because I know what the distances are across it. Well, radio waves work a lot the same way, to where the higher the frequency, the more data points you're going to get inside of 1 second. All right, now that means that you're going to have a clear picture, a higher data fidelity of that transmission, but it comes at a cost. Is that high frequency takes a lot of energy, and it can only go so far, and so you need more and more energy to go further and further. And so what you'll get with HF radios, you get a lot of range. You can listen to stuff way far away. So for instance, the last time I played around with HF, I was doing an HF radio check on a KC-46 on the flight line in Tukwila, Washington, which is just south of Seattle, like by 5-10 minutes. All right, and I was listening to the atomic clock timer go off in Colorado, which is like in like Colorado Springs, if I remember right. And so you think from Colorado to Seattle, and I was hearing it fairly clear. I mean, it wasn't really that bad. It was scratchy because it's HF, but like you could still hear it. So that's how far that went. But like you weren't going to be able to have like a really super duper robust conversation with anybody to be able to hear it super clear. You could just hear the clock ticking, and the top of every minute it would say like it'd go beep and then tell you, this is the such and such clock. It's 8:01 or 8:02 or whatever time it was, and even that was kind of scratchy. So that's kind of like the HF radio. You'll see HF radio get used a lot in overseas trips. If you're flying in an area where there's just not a lot of radar coverage or there's no one there to talk to, like if you want to go there's a great YouTube video where you can watch, I think it's like Norwegian Air flies from Norway over the top of the North Pole to like, I don't know, like Seattle or something, but they're doing HF radio checks it's like every 30 minutes, and what that does is they pick up the radio and they say like, hey, look, this is flight such and such, and we're at this place or at this coordinate, and then somebody on the other end is saying like, yep, we hear you, and that lets everybody know that, hey, look, that plane is at this point and it's going on just fine, and there's no other way to really track it. Now that's starting to kind of change with a lot of like satellite communications and things like that a lot of this is kind of like going away, and that's just the nature of avionics. Is that it changes by the time it gets implemented. There's a new change that's kind of coming down the pipe, and so you have to be the kind of person that just enjoys learning about this stuff because you're going to be constantly on top of having to master the thing that's in front of you while staying aware of the thing that's coming down the pipe. But anyways, that's HF radio. HF radios are a lot of fun to play with. If you ever do so like ferry flights, like if you wanted to put a like I was working on a Quest Kodiak, we were putting fuel cells in them to fly them across the Pacific to Japan. And one of the things that we had to do, because there's no radio communication and it's not equipped with any sort of satellite communication system, it was install an HF radio into it. And so you could very well do that. You can watch YouTubers that will fly, like Cessna 172s from Hawaii to California or crazy places like that, or these crazy distances. And one of the things that they always do is they always you'll see a HF radio that's been kind of rigged into the aircraft, so that way people can communicate with them if they get in trouble or whatever else. They can kind of say, "Hey, look, we're going down, and this is where we're at," so that way they know where the search party where to go look. Anyways, but that's HF radios. All right, so now the next band is VHF, and that's going to be the busiest. So like the most common one you're going to know about is FM radios. So like if you tune the radio in your car, and you might be younger and always just had an iPod or whatever, but used to you had to like turn your radio into like the local news station or radio station or whatever. But that gives you 88 to 108 megahertz. That's what that is. Marker beacons, VHF nav, and VHF com. I'm going to spend most of our time talking about VHF comms and VHF nav. Now, VHF comms go from 118 to 137 megahertz. That's going to be your most common radio frequencies that you're going to use as a pilot or a mechanic. You think about like the radio frequency on Texarkana is something like 123.5, if I remember right. So that fits right there in between that 118 and 137. And you'll end up toning into those radio frequencies to get whoever it is you're trying to talk to. Now VHF nav, you'll see it right there to the right of it. It'll say VOR in brackets. VOR stands for VHF omnidirectional reference, and it goes from 108 megahertz to 118 megahertz. Now, what does that mean? So we'll talk about VORs here in a little bit and kind of our breakdown what it is, but essentially it's a radio frequency that gets broadcast in 360 degrees, so that way you can navigate to a certain station. So what you'll do is you'll tune the VOR to the frequency of the VOR, so that your VOR receiver inside the cockpit, you'll tune that to the VOR on the ground, and you'll fly either directly to it, or you'll use that to help triangulate exactly where you're at and where you're going. And that was for whenever I was a teenager. That was the navigational system. GPS really wasn't out there yet. And so, all right. So going up to the above 300 megahertz, you have glide slopes, DMEs, and transponders. Okay, so a transponder, we're going to talk about that. We have a whole ACS code to cover on transponders, so we won't spend a whole lot of time on there. But transponders have to they transmit the data that of like, hey, look, this is who I am, this is where I am, this is the altitude that I'm at. And now with ADSB, it can translate a lot more data, like how fast I'm going, all the good stuff. And it puts that information out, so that way ATC, flight service, other airplanes can see who you are, where you're going, and where you're projected to be in the next couple of seconds, so that way they can help do traffic avoidance. DME is distance measuring equipment. You'll see those. Once again, like on a MMR, it's DME is integrated into it, so you'll see that still on heavy commercial aviation. But like DMEs, especially in the GA world, they're kind of going away if they haven't gone away completely. Essentially, they're just another radio navigation aid. What they do is, instead of telling you where to go, it tells you how far you are from the station. So if you think about it, if you have your sectional chart out and you say like, okay, well, I'm 100 miles from this station and 200 miles from that station, you take your little compass, like World War II style, and you can say like, oh, if I'm 100 miles, and you do like a circle, and then from that one place, and then you go to another one, like, but I'm 75 miles from this one. You adjust your compass so that way it matches the scale on the on the sectional that you're 75 miles away and draw another circle, eventually you kind of get this Venn diagram effect where like the only place that you could potentially be that's the same distance or those distances from those two places are right here in this little narrow band. So you're somewhere in there. The more DMEs that you have, the more you can tune into, the more accurate you can make your position, so that's what it is. But you, generally speaking, you won't really see those as much anymore as you used to, just because we've got better technology that replaces it. You don't have to do so much math and guesswork. The glide slope, though, it's on its way to being replaced because GPS WAS, you can do GPS approaches now to airports, and so that will slowly become the kind of gold standard for instrument approaches. But there are still a lot of places that do RNAV approaches, Texarkana being one of them, and the glide slope is basically, and we'll get into this a little bit more in a subsequent class, but what effectively it does, it transmits a radio frequency that degrades and changes, at different points. So that way the airplane knows, hey, look, I'm below the glide slope, I'm above the glide slope, I'm on the glide slope, and so that way, as you progress in towards the runway, you can just basically it becomes kind of like a little homing beacon, so that way you can fly right to the end of the runway. And anyway, so that's another RNAV. And when I say RNAV, it's radio navigation, is short for it. But so that's the 300 megahertz range. Now, if you look up into the 3 gigahertz, so like keep in mind, information fidelity goes up with frequency. So that means that like you'll get better, more clear information with the more data points you have. Those data points are the top of the wave, the sine wave of the radio frequency. So when you think about GPS, you're transmitting a lot of very specific information extremely fast, and you're having to do it's rolling over on top of itself on a regular basis. You think about a plane that's flying, you're looking at it on the GPS, and it says like, I am at point A. Well, after you look at it, it's kind of like Schrodinger's cat or whatever, Heisenberg's uncertainty principle. Like the next second is like everything has changed because the plane is moving, and so it has to transmit that information. Like, well, now I'm here, and so in order to do that, you need to have a high fidelity radio wave to transmit all that information. GPS is the way to do it, and so like that comes in at 1.6 gigahertz. Radio altimeters. So it's a radio altimeter will basically tell you how far you are above the ground. Think about it kind of like almost like a Doppler radar system on the bottom of your airplane, and or a sonar. You're thinking of a boat. Sonar is probably a better mental model. Like if you're saying like, oh, we're like it's 10 feet to the bottom. Well, it's transmitting a sonar wave. It's hitting the bottom of the lake and then bouncing back, and the boat is saying like, oh, well, that took like a second, so therefore it's 10 feet down. Radar altimeters, exact same idea, except for just using radio waves, and so it will turn around and tell you exactly how far you are. It's really big in helicopters, but they're also you'll find those on heavy commercial jets. You'll find them on a lot of different applications. Radar altimeters are extremely useful to let you know exactly how far it is from the ground, because keep in mind, your altimeter could be off because of air pressure and things like that, whereas the radar altimeter is going to give you the legit, this is how far it is to the ground, period, and let you know that. All right, but anyways, the radar altimeter is coming at 4.3 gigahertz, and then you have Doppler radar, 8.8 gigahertz. So if you're familiar to looking at the news and seeing like the Doppler, like that's what that's at, and the weather radar on like the nose of your airplane. What it's doing is it's taking radio waves and it's shooting them out and saying like what kind of return, what kind of bounce back it gets of those radio waves, and then it'll interpolate that to be different densities of clouds or types of clouds, so on and so forth. And so that's your aviation uses for the different radio frequencies on that. Okay, so one other radio system that we want to talk about is SATCOM. Now, SATCOM is just short for satellite communications. Now, when we talk about frequency, it's going to use the same type of setup as like your VHF or like your GPS radio. They're going to use a radio frequency to carry the data. The things that makes it fundamentally different is that now a satellite has been pulled into it. Now, most airplanes with like a VHF radio, if you look at the graphic, like the business jet or the commercial jet, will talk directly to the ground station. Now, that has its advantages and it has its disadvantages. It's simpler, so that's the main advantage, that like you can just talk directly to that guy. There's no intermediary. The disadvantage is that you're really limited on terrain and you're really limited on distance. So terrain, like if you say like there's a mountain in between that commercial jet and the ground station, it's really hard to talk, to send a radio frequency through the mountain. Or even if they're in one of the two of them are in some kind of like bizarre weather situation where like the weather is really kind of degrading radio communication. Um, then you have distance. Like the radio frequency can only go so far. I mean, yeah, you can get HF and you can go a long ways, but eventually it gets to the point where you can't really understand what each other's saying. And if you can't really understand what each other's saying, then you're not really communicating, are you? And so the question became like, okay, well, what do we, how do we fix this problem? And it became pretty easy. You just put a satellite up and you transmit directly to the satellite. And then once you have enough satellites in orbit, the satellites can relay information around each other. So if you remember from Independence Day, this is the what David at the very beginning of the movie realized the aliens were using their satellites to help coordinate the attack. They were bouncing the signals off of different satellites to get around not having you'll call line of sight, or LOS, line of sight with each other. So line of sight means that like you should be able to, in a straight line distance, see the person you're transmitting to. So if they're on the other side of a globe, they can't, because there's a globe in between the two of you. So you need to have a relay station, and the satellites in that movie provided that. Well, that's exactly how SATCOM works. And so when you have like a higher frequency, a higher fidelity carrier wave that you're talking to the satellite with, you're gonna have more clear transmissions, and you're gonna have a higher level of data that you can transmit to the satellite, and then it'll then relay it down to whoever it is that's supposed to be receiving it. And so that's how SATCOM works. It like will seem to be more complicated than what it is, but that's boilerplate. That's all it really comes down to. Now, typically on satcoms, especially on older planes, you're gonna do you'll do kind of like almost like a text message kind of thing. You can talk verbally, but like it generally speaking, like what they'll end up doing is that they'll send text messages back and forth, and as the way things seem to be progressing, since computers can read the text messages far easier than they can with the audio messages, it seems that like that's becoming more and more the case, that eventually you're going to listen to ATC and you won't hear anything because it'll all be text messages from one airplane to the next. Yeah, so that's SATCOM. Okay, so let's talk about like how do you actually put information on a radio wave. And it's not hard to make a radio wave. It's really comes down to having a power going to an antenna with an oscillator in between the two of them, and you'll create a radio signal. There's naturally occurring radio signals out there. If you want to go, kind of see what that looks like, go watch the movie Contact back from the '90s, and that's what all of that's about. But how do we use the radio wave so that way it actually transmits something useful? So I want to read you a little paragraph out of the 8083, and then we'll talk about it. It says the production and broadcast of radio waves does not convey any significant information, which we just talked about. The basic radio wave discussed above is known as a carrier wave. To transmit and receive useful information, this wave is altered or modulated by an information signal. The information signal contains the unique voice or data information desired to be conveyed. The modulated carrier wave then carries the information from the transmitting radio to the receiving radio via their respective antennas. Two common methods of modulating carrier waves are amplitude modulation and frequency modulation. Alright, so what does that mean? So it means that, like, if you're looking at the graphic on the screen, you have the carrier wave. Now, all that is that's just a wave, a radio wave that is being transmitted out there. Now, once again, it usually has like a power source, an oscillator, and then an antenna that creates that transmission. Now, once you've created the transmission, you have that wave. You need to be able to modulate it in either through amplitude modulation or frequency modulation to create the data that you want to transmit. Alright, so what happens is that you take if you look in graphic A, there's a carrier wave, it's a standard radio wave, and then you also create another wave that basically holds that data. All right, that says like this is like a microphone. So you know what this sounds like, whether or not you realize it or not. If you ever remember like going to like your high school auditorium and somebody's going to say something into the microphone, they turn the microphone on. There's like a slight hum, like in the background. That's the carrier wave is there, but it's not modulated by any way, shape, form, or fashion to actually transmit anything. But then somebody steps up to the mic and says hello, and all of a sudden now like their voice that just says hello is now being amplified greatly by the microphone, the electronics, and all that good stuff, and coming out the speaker. And so what you've done is that you've taken a carrier wave, and then you've spoken, through we'll get into how the speakers work here in a little bit. You've spoken another wave into existence, and you've combined the two. Now, what they're not is that they're not two separate waves. They're now one wave. You've had two separate radio waves that have come together and made a baby, and since like that new baby is the radio transmission that's actually coming out. And so on that bottom graphic that looks like this big kind of like amoeba-like deal is an amplitude modulated carrier leaving the transmitter. So in other words, what's happened is that like you have, dad carrier wave and mom varying DC audio information there in A and B, and the baby that comes out of that is C, the actual amplitude modulated transmission wave. Now, there's another way that you can. This is amplitude modulation or AM modulation. There's another one called FM modulation or frequency modulation. Okay, this graphic will show us what a FM modulated signal looks like. If you'll notice, it's very different. So the carrier wave, looks very similar. Then you have a modulating signal that gets married up to it, and the child signal that it produces looks very similar to the carrier wave. What's changed is that the frequency has just expanded or contracted, allowing for the maintenance or the maintaining of that same level of frequency. Okay, now why does this make a big difference between AM versus FM? So FM allows for a clearer signal to be transmitted, but over a shorter distance. Now remember, just like we were talking about, like data points, before, if you compare and contrast those two graphics, if you pause and then were to roll it back, the data points, so the peak points on both of those waves are very different. The AM signals will go further, so you'll see a lot of like AM radio stations in really rural areas, like places like mountains and things like that, because you can get more bang for your buck on transmission by transmitting further and further out. The downside of it is that you'll have a lot of noise and scratchiness and things like that because you don't have the same level of data fidelity per second of wave as you do with FM. But FM, on the other hand, whenever you're in range and you're with close enough to the radio station, you're going to hear everything a lot clearer. So it makes for a better radio station. That's why most radio stations are always FM, because they're located inside of cities and stuff. They don't need the distance. What they really need is to be clearer and more entertaining to listen to be able to sell like advertising dollars to people that are local around you. And then obviously the higher data fidelity that's needed for the use of that radio, the higher frequency that you need. The higher frequency that you need, you're going to end up running into more expensive components with a lot more power. And so that's something to keep in mind. But that's the basics of frequency modulation on AM and FM. Okay, so that's all in the transmission side. What about on the receiving side? So somebody keys the mic, says something, it goes somewhere. That signal is then received somewhere else. What does that look like? So this is a process called demodulation on the AM side. Now this will look very similar with FM, so we're just going to stick with AM for right now. So if you look at graphic A, you have an amplitude modulated carrier in the receiver. It's been transmitted. It's out there. Somebody's received this big, like electromagnetic amoeba looking thing. And what's going to happen now? Well, the next thing thing, you're gonna get it's been detected by a modulated carrier. So you have your AM radio, it actually grabbed it. The next thing that's going to have to happen is that that carrier wave is going to be removed from it. So we're going to say, like, we had your carrier wave and your DC modulated wave that came together and made a baby into what was received there in graphic A. We're going to take the carrier wave off, and so all that's left is the demodulated signal, and then from there that gets piped into a speaker, and it actually comes out as noise, because what's happened with the speaker is that as that wave oscillates up and down, it actually moves magnets inside of the speaker that's attached to a diaphragm, and that moves air and creates vibrations in the air, which we then interpret it as sound. And so, even though looks like it's really really complicated, a lot of this stuff is really not. Like, you have a carrier signal on a transmitter in your hand. You speak into it. The vibrations from your voice hit a diaphragm and causes a little magnet to move up and down, which causes a new radio wave inside of a speaker, or inside of a radio. As those electrons pass by each other, electrons get pushed into the wires, which then gets introduced into the radio, and then married up with the carrier wave as it's transmitted. As that happens, it just goes across the world, I suppose, and then hits the radio wave, where the exact thing happens but in reverse. And so now you have a wave that's coming into the radio, gets stripped of the carrier wave, and then all that's left is like the little pulses that the original microphone had placed into that wave, and that comes out as as speakers, because it moves a little magnet up and down, which moves a diaphragm, which then produces vibrational waves inside the air, which then we hear as sound. It's really not that overly complicated, but that's how AM and FM modulation and demodulation. Okay, so another thing I really want to impart to you is basically a definition of what is a single sideband. Now, this won't have a whole lot of impact on you troubleshooting or installing or anything else like that, or even really operating. But you'll hear like SSB radios or single sideband radios, and you're going to wonder like what that is. Well, here's the problem: is that as time has progressed on, we've used radio waves for all kinds of things. But the problem is that, like, if you have somebody's transmitting on frequency A and somebody's receiving on frequency A right next to them, then that radio signal is going to come through on the second person, they may not have the same end goal in mind, and so next thing you know, you're going to have to change frequencies. You're going to change different stations, all this good stuff to try to help divvy up the electromagnetic spectrum. Now, the military deals with this, and they call it like spectrum management. It's like a big task, because you have all of these people, all these different radios. If every squad has a radio, and you have an entire division on the ground, everybody's transmitting on different frequencies, trying to not step on one another. So that way, because I don't really care what the guy 10 miles down the road is doing. What I really care about is that the guy that 1 mile down the road that I'm working with, I really care about what he's doing, and staying in constant communication with him. Well, to prevent that problem, you have this problem of spectrum management, and single sideband radios tries to help get after managing that spectrum effectively, by effectively basically cutting off half of a signal, so that way you can use that other half for something else, and you don't necessarily step on one another. So let's look at another graphic. All right, so here's the thing: you don't necessarily need all of that bandwidth, and so in order to be as economical with the bandwidth as possible and help deconflict as much of the spectrum as possible, the lower sideband is actually what ends up getting used. Here's from the 8083. It says, in lower frequency ranges, such as those used for ground wave and some skywave broadcasts, single sideband transmissions are a narrow bandwidth solution. Each sideband represents the initial information signal in its entirety. So it means that the upper sideband is basically an echo of the lower. So therefore, in the single sideband broadcast, the carrier wave and either the upper or lower sidebands are filtered out. Only one sideband with its frequencies is broadcast, since it contains all of the needed information.
This cuts the bandwidth required in half and allows for more efficient use of the radio spectrum. Single sideband transmissions also use less power to transmit the same amount of information over an equal distance. Many HF and long-range distance aviation communications are single sideband. All right, so whenever you start talking about avionics, a lot of people think there's a lot of high-level math into it, and there definitely is on the engineering side. On the maintenance side, you generally don't see it, except for in the land of antenna lobing. Antennas are a world unto themselves. If you want to go be a gazillionaire, go get your electrical engineering degree and then specialize in aircraft antennas, because there's not that many people that are doing it out there, and it's actually really, really complicated. It is very math intense, and it really kind of dictates how a lot of systems will operate, and like you can do all kinds of crazy things with antennas if you know what you're doing. So we're gonna give you like an overview of like what an antenna lobe is and why antennas are selected for why they're built a certain way as opposed to other ways, and we're gonna let you kind of chew on that. Don't expect just a whole lot of this on your test, and most on the maintenance side of things. Once you get to where you're going, you're going to say like, hey, here's an antenna, it's bad or whatever. We're going to take that off. We're going to put the same part number back on. And that's really kind of the extent of which they are going to expect you to be able to do anything. So if this stuff is just like way over your head, just survive it and go on, and it'll be okay. If this interests you, you really need to dig into it, because this is an area where you can really you can be pretty profitable if you tailor your resume to it. Okay, so in order to fully understand antennas, let's talk about some radio basic like components, not on like the micro scale, but on the macro scale. Now, whenever radios first came around, you had a couple of different types, and now there's basically like one type. So you have transmitters, and these are radios that transmit out. And then you have receivers, and receivers are pretty common. Like you think about your car is a radio receiver. You're not gonna necessarily transmit unless you have a CV or something like that. But like just a receiver basically just does that. It's just a station that just receives and receives radio waves and then makes them into sound, so that way you can understand what people are talking about. But by far and away, the most common one is a transceiver. That's what's actually in most of your aircraft now. It's what's on the screen, both a handheld and inside the aircraft transceiver. And all a transceiver does is it does both. It basically can either receive or transmit, and so therefore it becomes a transceiver. That's something that you should know. Okay, let's pretend like you're an engineer and you're going to select an antenna to go on the end of a transceiver and get mounted to the top of the fuselage, and so that way you can transmit out. What are some of the things that you're actually going to think about? There's three main characteristics that you have to pay attention to when selecting an antenna, or whenever you're just simply operating antenna. You got to make sure you have the right antenna that has these three factors optimized for its use. One is length, the second is polarization, and the third is directivity. So those are the three fundamental traits of any antenna. And so the first one we're going to talk about is length. So when an AC signal is applied to an antenna, it is a certain frequency, which we know. There is a corresponding wavelength for that frequency. An antenna that is half the length of this wavelength is resonant, and during each phase of the applied AC, all voltage and current values experience the full range of their variability. Now, as a result, an antenna that is half the wavelength of the corresponding AC frequency is able to allow for full voltage and full current flow for the positive phase of the AC signal in one direction. The negative phase of the full AC sine wave is accommodated by the voltage and the current simply changing direction in the conductor. Thus, an applied AC frequency flows through its entire wavelength, first in one direction and then the other. This produces the strongest signal to be radiated by the transmitting antenna. It also facilitates the capture of the wave and the maximum induced voltage in the receiving antenna. All right, so that's a lot, but essentially what it means is that there's a precise length that is optimized for any one AC signal. that will allow it to have the most bang for its buck.
Now, oh man. Now, if you have too much antenna out there, it will actually work against you rather than for you. But if you don't have enough, you don't maximize the amount of energy that actually is in that AC wave to transmit. Now, the graphic that you're looking at actually kind of basically says this exact thing. It says that, hey, look, if you have the entire wavelength, you divide that by 2, and that will give you the optimized antenna length for a set channel. Now, where this gets complicated is that wavelength will change depending on the frequency that you're using. So, you imagine a multi-mode receiver that can be dialed up or down, into different frequencies, which is pretty much all aircraft radios. I can't think of a single frequency radio that's out there other than maybe your ELT or something. But when you look at that, like, it's not really practical for you to have multiple antennas, and so what they have elected to do is essentially like you create one antenna that will generally work pretty well. And then now when you do the math on like a lot of your VHF comms, you're only down to like 3.96 to 3.44 feet of variance. It's not really that big of a deal. And then you put capacitors in there, or a variable capacitor in there, to help self-tune as you change frequencies. So as you go up in frequencies, the capacitors react, so that way it can electrically lengthen the antenna effectively. And then as you tune it down, well, then the capacitors will operate in a way that electrically shortens the antenna and allows for an optimized transmission. But it's nothing to really get your brain super wrapped around. This is just kind of like for your professional knowledge that like length is a big factor with antennas, and so it's something that you want to keep in mind. All right, so the next factor we need to take into consideration is antenna polarization. So antennas are polarized. They radiate and receive in certain patterns and directions. The electric field caused by the voltage in the conductor is parallel to the polarization of an antenna. It's caused by the voltage difference between each end of the antenna. The electromagnetic field component of the radio wave is 90 degrees to the polarization. It's caused by changing the current flow in the antenna. As radio waves radiate out from the antenna, they propagate in a specific direction and in a specific pattern, and that's called the antenna field. This orientation of the electric and electromagnetic fields remains 90 degrees to each other, but radiate from the antenna with varying strength in different directions. The strength of the radiated field varies depending on the type of the antenna and the angular proximity to it all. All antennas, even those that are omnidirectionals, radiate stronger signal in some directions compared to other directions, and this is known as the antenna field directivity. So, that's a long-winded way to say that, like, your antenna, it can be, it's going to have a certain lobe pattern. So what you're looking at is like a lobe of an antenna that comes around. So that's just a like a stick style antenna that's just coming up like a wire, but it's transmitting outward. And now, in all directions, some are not equal in its power to transmit. So you notice this one kind of like east northeast is stronger than it is in other places inside of that lobe, and the reason being is just by the nature of the AC signal that's being pumped through it. It actually has just a little bit more juice than it does in other areas in that east northeast direction. Now, why and how does it matter? Well, in particular case, with this omnidirectional antenna that's right there, it really doesn't matter that much. There's a couple of implementations that you might be able to use in flight, but it would be very, very, very slight even if you did. For the most part, it's inconsequential. However, whenever you start getting to specialty antennas or certain types of antennas, that can make a big difference. You can turn around and design an antenna so that way it is optimized for the person or the people that you think you're going to be reaching with it. Okay, so this is another aspect of antenna lobing or in this case polarization. Whereas the diagram that we just looked at was a vertically polarized antenna. This is a horizontally polarized antenna. Notice that the lobing, instead of going on side to side, it goes top to bottom and wraps around. That's called it's called antenna polarization. It's just another aspect of the way that you build the antenna will will dictate on how it projects its signal into the world, and something you need to keep in consideration whenever you're either designing or installing an antenna on an aircraft. Okay, so here let's look at Yagi antennas. Yagi is just a type of antenna that has a very specific, very directional antenna lobing scheme that allows you to basically point exactly where you want that signal to go and not have to worry so much about anybody like necessarily getting the signal that you're projecting off to the left or the right or wherever. You basically can aim the antenna like a gun and shoot a signal directly to whoever you're talking. All right, so this is what it looks like. There's the Yagi on the top left-hand corner. There's to the right of that is kind of like the three-dimensional breakdown or the pattern of how the antenna lobes, and then the other two kind of like give you like a two-dimensional plane and kind of give you an idea of what that looks like. Now, in the example that we just looked at was military. There's very obvious advantages to that. Like you can send a signal directly to the person you want. You don't have to worry about somebody else kind of listening in. If they if they were having to be nearby, so you can kind of transmit and just shoot it past the enemy that may be close by. But there's other opportunities or other reasons why you would want this as well. Like if you have like limited radio power and you know exactly where the person is that you're trying to transmit to, you might want to have that antenna set up on top of your shed and aim directly at the next place that you're trying to talk to and shoot that off. This isn't really that different from the way an ILS works. They have very specific antennas that shoot a very specific antenna lobe pattern directly to the airplane. The airplane just flies it on down. And so this is how powerful this stuff can actually be. It can work really, really well if you understand how it operates. Now, you as mechanics, maintainers, avionics guys, your job is just to kind of understand what right looks like. Your job is not necessarily is not necessarily ever going to be to design and do any kind of engineering, even though you may get into that, especially if you get into the experimental world or anything like of that nature, anything where things are a little bit undefined. Having this knowledge in your back pocket and having an understanding of how things work can be really, really helpful in certain situations. Okay, now that we understand how radios and antennas and all that works, let's look at a couple of specific antennas on the 737 MAX and see what they look like. This is a marker beacon. It's one of your radio navigational aids that we're going to talk about here in a later class. But notice that it looks like just a long blade that just runs down the side of the fuselage. And so that's something that's kind of unique. And you'll notice that all of these antennas are uniquely built to do what we want them to do. It's not just simply sticking a wire to a radio and calling it good. There's no place better to see that, the uniqueness of antennas than right here. The glide slope antenna, just like the little shark fin, but the localizer antenna looks like a hoop that goes up on the vertical stabilizer. And then the VOR slash localizer antenna looks like just like a little blade. Each one perfectly built to gather the information or transmit the information as needed. Here's a DME, looks like a little shark fin. The ADF is just a hockey puck. It's just basically needs to just gather whatever information we can. These are very unique. So this is the radar altimeter antennas. Notice that they have to be going a certain way. They can't be painted or obstructed in any way. And so you'll walk underneath the airplane, you'll literally see just this little square white antenna that's buckled up to the airplane. And that's because if there's anything that gets on them, it will mess up the way that the radar altimeter operates. And that's something that you need to be cognizant of, that antennas, generally speaking, aren't painted. Sometimes they are, and it just depends on what the use for that antenna is and what the job demands are on it. But radar altimeter antennas absolutely do not ever. Same thing for GPS antennas, where these are really going to be really different. Is that these go on top of the fuselage, whereas radar altimeter antennas go on the bottom, even though they look very, very similar. GPS will also be more curved. Radar altimeter antennas are flat, but they look similar in a lot of different ways. But they generally should never be painted or obstructed, so that way it has a clear line of sight to talk to the satellites. And also notice the architecture of the system, how the MMR basically talks to everything, and everything talks back to it. That's how complex some of these navigational systems, especially, can get. Now, something that will look a lot like antennas but are not antennas are static wicks. You'll be very familiar with them. They look like little bitty antennas that stick off the edge of the wings. And then what's happened with these, or what these static wicks are for, is to provide a way for electrons to leave the body of the aircraft. Now, with all this radio frequency that's coming or going, the there's a lot of extra electrons that get built up onto the skin of the jet. Now, if you were to like land and you didn't have any static wicks and you didn't ground it and you walked up there and were to touch the jet, it would likely shock you, perhaps even fatally. When you're sling loading, with helicopters, part of the operation is to ground the helicopter. You take a big, like, it looks like a shepherd's crook that goes to a grounding rod, and you touch the helicopter, so that way all of that extra static electricity can come off of the helicopter. That's how dangerous this can be. And static wicks provide a way to channel all those electrons out of the body and back into the atmosphere. Now, the way they do it is that they have a small, almost like broom-like construction at the very tip of it. Some of the older ones literally are like, they're these graphite. I don't even know, almost looks like yarn hanging out of it. The more modern ones are still stiff, so that way they maintain their edge as they fly, and they don't fall apart on you or anything. And what they end up doing is that all the electrons will basically go to wherever there's like a negative space for them to flow to. By exposing that wick to the air, you're effectively making an electrical connection with the air and pulling the electrons out of the jet or out of the jet's skin primarily, and then back into the atmosphere, and that lowers the chance of a static discharge ever happening. But the more radio traffic it happens on any aircraft, the more likelihood that you're going to end up having a static discharge happen. This becomes very, very important for your safety, but it also becomes very important when we're handling any sort of electronics. Because remember, our ESD practices, that's there to help curtail some of this accidental static damage that could happen whenever you're pulling boxes out of an airplane. All right, one more system that we need to talk about specifically on heavy commercial aircraft is the Interphone or PA system, sometimes called the Intercom systems. It's basically comes down to being able to talk inside of the airplane. Now you think about like a 777 or an 87, 747. You're talking about a huge airplane, and things could happen that like you need to address the crew, the flight crew, or the cabin crew immediately to let them know, hey, look, there's something happening that we should call attention to. Maybe it's a safety issue. Maybe it's just a state of flight. Hey, look, we're 10 miles out. It's time to start prepping the cabin for landing. And it's really impractical to stop what you're doing and go run to the other end of the airplane to do it, or maybe it's unsafe. It's just going to take too much time. And so most heavy commercial aircraft have a audio control panel that links to multiple ways to talk to each other. So we're going to take this from the Max, and we're just going to kind of walk down that left-hand side and talk about when and where those things could be addressed. So first off, you have the control wheel microphone switches, and that's going to go to your headset, which is the not David Clark ones, the black ones that are the second one up, for the crew. Now that's going to allow us to talk to the tower. It's going to talk to everybody else just like you would with a regular radio. But you can also put it on speaker and address everybody that's in the cabin, or you can call the external power panel, or call the flight attendants, and they'll get like a little flashing light on their handset, and they'll pick up and they'll talk to you. And so that's what that's for. You also have hand mics on all the aircraft. You don't need a headset. Most of the times you just pick up a handset and talk that way, just like you were in like a police car or something. Most of the time, as a avionics guy or as a maintainer, that's what you're going to use because they stay permanently affixed to the aircraft. You're not going to have to run around and try to find a set of David Clarks and talk to them. But if you're going to be flying or going to be doing it a lot, the headset actually is the way to go. You also have radios that are piped into the oxygen mask system, so that way if there's an emergency and the oxygen mask gets deployed, then the pilots can still be able to talk to the ground crew. The one that you're going to use the most is the P40 panel, or I believe it's the P40 panel, but it's the external power panel headphone jack. You'll plug up to it and basically call the flight deck. The flight deck can then talk down to you. So you can say, hey, look, this is going on with your engine or whatever it is you need to talk to them. And so you'll spend a lot of time using that for sure.